Hello everyone. Welcome to today's webinar, Cost-Effective Metal Part Printing, a Use Case with L3Harris. My name is Claudia Kretz and I'm the moderator today. First of all, I would like to let you know that you can send your questions for today's presenters via email, and you will see the contact details at the end of the presentation. In today's webinar, we want to focus on cost-effective metal part printing. Here with me is Ben Rader from BASF 3D Printing Solutions and Mark Holthaus from L3Harris to give you more insights into the L3Harris use case. Ben and Mark, can you please introduce yourself?
This is Mark Holthaus. I'm a lead designer and additive lead for L3Harris fusing and ordnance systems. I've been involved in rapid prototyping and AM technologies for over 20 years. At L3Harris Infusing Systems, we develop and manufacture electronic and mechanical fusing systems and height of burst sensors. These are precision timing devices. These devices contain high tolerance and high precision parts. And we also have a manufacturing facility where we require a lot of complex tooling.
Great, yeah, thank you, Mark. As Claudia mentioned, my name is Ben Rader, and I'm a business development manager in our additive extrusion systems team. I joined BASF Forward AM back in June of 2017, just over 3 years ago. At that point, as of last year, January 2019, I joined the Additive Extrusion Systems Group, but have been working in the additive manufacturing industry since 2008. I know a lot of people who are on the call today are probably pretty familiar with our UltraFuse 316L. Many of you may already use the filament also, but for those who aren't, I thought a really quick overview might be helpful. So UltraFuse 316L is our metal filament offering. It is a stainless steel material. It follows our general philosophy of being machine agnostic, as in this material can work on most, if not all, of the open FFF printers. By that, I mean printers that do not require you to use the machine OEM's direct filament. So we've got customers that are working with a wide range of machines. Some of them are going to be a little bit on the higher end side, as well as people who have actually purchased and ordered kits online. They've all been able to get good parts that were nice stainless steel parts. So because of that, you do get a low investment cost of the printing hardware, primarily because you get to not only pick the machine you want at the price point you want, but potentially already use machines that you already have in your shop. The material itself does print really nicely. It does have easy handling. As you can see on the left, there is the spools of the material. It comes like any other filamentized material. You're able to use it, store it, process it just like you would any of your other filaments that you're currently using. You do also get reliable filament quality that you would expect from BASF. Part of that is because the material itself is actually based off of our Catamold material. That is our material that is used for metal injection molding. So with it, you can also do lightweight designs. That is a nice feature because you can actually have hollow parts as well as do infill on your parts, really taking advantage of some of the unique possibilities that FFF printing has to offer. And then we also utilize industrial debinding and sintering solutions for the material. So part of the reason for that is, as I mentioned, it is based off of our Catamold material. So it follows the same post-processing process where it uses our catalytic debinding and sintering. So if you have capabilities in those ovens already in-house, or perhaps you already use our Catamold material, what you can actually do is process your own parts. If not, we do have a debinding and sintering network already established where you can actually go ahead, print your parts on your printer, package them up, send them out to one of our partners. They will actually do the debinding and sintering for you through the catalytic debinding and sintering process and send you back a stainless steel part. So we do have a global network already established for that. Here in North America, we work with DSH Technologies, who is located out of New Jersey. So with that, I'm going to turn it over to Mark.
Thanks, Ben. For us at L3 Fusing and Harris, L3Harris and Fusing Systems, additive metals for us started out with a beta program. In the program, we had 3 partners. We started with BASF. I contacted Ben Rader and we talked about the material and the possibilities of printing with it. Shortly after that, I met folks at Cincinnati Incorporated and we acquired one of their machines. So we then had the capability to print green parts and tooling. Through BASF, we added DSH technologies and we were then able to produce metal parts and tooling. The beta program approach allowed us to enter into and learn about what it took to be successful with this type of metal printing. We had been researching various metal AM systems and wanted to get into additive metal parts when we became aware of the BASF ultrafused material. We wanted to explore more sustainable solution than using plastic AM that in many cases had limited life. We realized we had an opportunity to basically accomplish this with BASF in Cincinnati and DSH Technologies. We first started out successfully printing green tooling, and then DSH did the debind and sintering, so we had dense metal tooling. We then moved into printing product development parts, and shortly after we got started, we upgraded to the Cincinnati HT printer. The HT printer has a controlled chamber, and what we found is a hotter chamber can assist in maintaining layer adhesion, especially when printing tall parts, and it has allowed us to surpass the standard guidelines. The graph shown at the left for the HT machine, that shows what the machine's capable of. We're not printing the ultrafuse though at that temperature. We're running the hot end at 240 C, the table at 100 C, and we've got the chamber running at 55 to 70 C. The controlled chamber also allows the humidity within the chamber to drop to 10%. The nozzle we're using to print with is 0.4 millimeter. We made a decision early on that we did not want to get into the debind and sintering business. We just didn't want to have that on site. So DSH became our debinding and sintering partner for metal parts and tooling. We looked at them as being experts in the debind and sintering field, and they're experts in injection molded parts and metal additive parts that we print using the ultrafused material. We generated a process map, and we called the process metal fused filament fabrication, and it basically uses the BASF filament in a fused filament fabrication printer again, and then the injection molding process used in debind and sintering technology. So we're going to use this chart, and we're going to take a look at some of the steps it takes to be successful in using this process. First of all, follow the design guidelines provided by BASF. There's a lot of information in there that you can use. It's a very good place to start. As you become more familiar with printing, you can enhance the parameters for your own specific parts and needs as you become more expert. But some things, important things here to mention, wall thicknesses no less than 1 millimeter or 40 thousandths of an inch. Wall thickness to feature height ratio is to be less than 3 to 1. We've been successful at going 5 to 1. So what that means is 3 to 1, 100 thousandths, about 300 thousandths high. We've been printing 185 wall thicknesses at an inch tall. The controlled and heated chamber seems to aid in achieving greater ratios. We started out with a chamber that wasn't heated, And we've noticed that since we have the heated chamber, we're able to increase those ratios. Uniform wall thickness, if possible. This helps to reduce stress in printing and centering. And you can do angled surfaces or angled undercut surfaces, but they should be 60 degrees or higher. The picture at the left there, it's 55.96 degrees, shows a part that we printed close to the 60 degrees. And then add fillets and chamfers. Suggest that you orientate parts during design as if they're going to be 3-axis CNC machined. It's just a good practice because you maintain the part scaling, compatibility with the green part printing, and also the sintering process and machining. So what that means is print orientation, same as sintering orientation, same as machining orientation. We found that to be a very good practice. And it is best to always debind and sinter in the same orientation as you printed the part. So don't print vertically and then lay it down on its side and do the debinding sintering. It's best to do the debinding sintering in the same orientation as you printed it. Teardrop side holes, they will become round after sintering. And remember, parts are scaled, so they'll be 20% larger than the design model. So the part design size, the green part size, will have to be considered in the capability of what your machine can handle. We had a part that after scaling was larger than the printer could accommodate sitting square on the table, and we had to actually rotate it to take advantage of the extreme corners. Recommended size is 4 inches or 100 millimeters, but we've been printing parts that are over 152 millimeters or 6 inches, and we've done some that are up to 7.5 inches. Manufacturing preparation. So what we do is we copy the design model and we create a manufacturing model, and we have the two linked. So if the design model is changed, our manufacturing model can be updated. It's just good. We found that to be very good CAD practice. When we prepare for metal manufacturing, we actually remove features like close tolerance holes and have them machined in later. We add features like supports to aid in printing, and sometimes also to add stability during debind and sintering. The picture at the left has features added to the end of the shaft and under the opposite end. We trim them off before we actually send it off to be sintered. For larger blocks, I would suggest that you add machining stock to the bottom of the part and machine it flat with the top surface after the part's sintered. But plan for as little machining as possible. Take advantage of the technology. Scale the manufacturing model per the BASF guidelines to start. Again, as you become more expert, you may start modifying them a little bit. And then generate your STL file. Recommended layer thickness is 0.15 to 0.25. Again, 0.15 to 0.2, I got inches, it's millimeters. Sorry about that. In the picture at right, the part is printed and sintered laying flat. The cylinder is printed oval shape and then becomes round after sintering. The threads are also printed. Due to the size of the shaft, it's 188 thousandths of an inch. We did not print it vertical, as we would require a lot of support structure that would need to be machined off. And we found that laying it flat and printing it in oval shape has been very successful for us. We created a spreadsheet here to track shrinkage so that we could get a handle on what works for us and how to get accurate parts. Remember, the material has weight and the parts are layered. So they may shrink differently than what you you've planned, or they may shrink differently than what you scaled your CAD model to, especially in the Z-axis. Also, different machines and room conditions may require unique scale values. So you may wind up having your unique values. We created a spreadsheet that helps us track what is actually happening here. So we start out with the start scale values that we started out with. We have our target design size, that's our CAD model size. Once we print it, we do measure the green parts so we know where it is. We send it out to be centered. Once we get the centered part back, we measure it, we enter those values into the centered part size columns, and we wind up with the adjusted scale value that we should have printed that part to. We can also use the same type of a spreadsheet for the green part. So in this particular case, we're waiting until we get the centered part, but you can effectively use this on the green part size to see whether or not your printer is actually giving you the exact size you thought you were going to get. And this isn't hard to create in the cells to do these calculations, so it's a very helpful tool. 3D printing. Of course, this generates the green part. And again, use the guidelines from BASF in your slice software. Of course, there you slice and generate your G-code program. And if your slice software shows a 3D representation of the toolpath, I would pay close attention to that, because extrusion with values can have an impact on toolpath quality. We've seen that several times here. The material comes dry in its package, but the environment for printing should also be controlled. So if you don't have a controlled chamber, you should really have your printer in an environment where the humidity is somewhat controlled. And we have found that the heat chamber does control humidity quite a bit. It helps keep layers together in taller parts. Catalytic debinding and sintering. So let the experts that are metallurgists do this. As you can see, there are several steps that need to be performed though. Catalytic debind the part to remove the polyacetal, that's the first stage. And then there's a thermal debind and sinter to remove the backbone polyethylene binder. So that's the how the process actually, the steps in the process and how they actually work. But I would contact DSH Technologies to get some specifics on it and to learn, get more detailed explanation of how this technology works. Machining. The block in the picture below, that's the one we've been seeing through this presentation. It holds the electronic contacts for assembly. So these contacts lay over each other and they drop into those various shaped holes you see in the block. We removed some very close tolerance holes that we machined in later. We did add material to the bottom and we machined it flat with the top. We used the holes on the outside are used to align the block for machining. The parts were printed Z up, sintered Z up, and machined from the top Z up. This is actually one of the first complex tool parts that we printed. The block size is 3 inches, about 3 inches long by about 1 1/8 wide and 1 inch high. Those little channels you see going down into square rectangle things, they actually angle underneath. So there's all kinds of geometry going on below the surface of the part. Traditionally, this part would be sectioned and all those little shapes would be machined in individually, and then the block would be fastened together with screws and dowels. So this is a big enhancement over traditional process. Printing examples. Again, this is the same block. It's been shown throughout the presentation. The 3 steps: the green, the brown, and the dense, then centered dense part there. A material cost about $66. Build time's 19 hours, and the sintering cost is $80. We could print 5 of these and send them off, and still have the sintering cost be $80. So it's a good savings. Here's a second example. This was the first attempt at design and printing this tooling fixture. What may seem simple here wasn't quite as simple as it looked, I guess. The part was designed with raft material added and a bridge across the U-shape opening. Okay, that was our first attempt at this. Then we trimmed the raft off before it went to DSH Technologies, and then we had it centered into a dense part. Material cost for this was, for quantity of 4, was, it's $10 in 3 hours to build them, and $80 again for sintering. And this is the final version of this same part, and we increased the bridge size across the end, and we added machining material to the bottom of the part, because we found that the bottom surface had to be extremely polished, highly polished, because this slides on a circuit board. So you can see in the chart here on the savings, material-wise, it cost more for the ultrafused material, but the manufacturing cost was a lot less. The number of parts we printed were 50. Of course, we had a debind and sintering cost and a post-machining cost, and the machining cost was to machine the bottom and then polish it and actually EDM the slot in the 50 parts. So we saved about $2,318 making 50 of these. We did a study on this part, and we wanted to learn some key aspects of printing and sintering for this type of geometry, and to see whether or not the features could be produced in the process. This chart below shows not only the fact that we can produce these features accurately, but what the repeatability was of the features after the part was sintered. You can see that the sizes are fairly consistent across all the dimensions that we measured. The parts were not printed at the same time, but they were sintered at the same time. Here's another example. We've seen the shaft, the part with the shaft there in other slides, but there's actually a threaded knob that goes on the end of that, and you can see it installed in the fixture there. This fixture is actually 100% printed, and very little, if no, machining is done on this thing. So we've replaced that part with a metal part because the plastic parts were breaking, and it's got a little spring in there. You pull it back and it locates a part in the fixture. So we're looking at, we're also reviewing other parts that we might want to print metal for this particular fixture, and then we're looking at possibly converting some of them over. Again, 4 sets of this fixture, or these metal parts, I mean, cost of $10.12, 5 hours to build 4 sets, and of course the sintering cost would be $80. I would start out with the BASF guidelines and then enhance them as you become more expert in printing, and learn as much as you can about what's happening during the debinding and sintering process. The more knowledge you get about all these things, the better off you're going to be. So.
Perfect. Thank you, Mark. We appreciate you taking the time to present and share your experience with the material. If anyone is interested in potentially purchasing or moving forward with the UltraFuse 316L filament, and you're located in North America, please, reach out to one of our North American distributors, M. Holland, Matter Hackers, or shop3d.ca. If you are not located in North America, because I know we may have some global participants on the call as well, you can actually reach out to us directly at the email address listed, sales@basf-3dps.com. We can actually work with you directly, or in many cases, we do have global partners and we could find someone who is going to be in your region.
Thanks for giving us some insights into cost-effective metal part printing based on the L3Harris use case. And again, if you have any questions, here you can see the contact details. So feel free to reach out directly via email. Also, we want to thank everyone for the attendance today, and thanks to Ben and Mark for taking the time.
But with that, we would like to thank you once again for your time and attending today's webinar. Also, a special thank you to Mark as well as L3Harris for participating today, in addition to Cincinnati Incorporated as well as DSH Technologies. Thanks again, and everyone enjoy the rest of your day.